Hello everybody. Today we will discuss two-dimensional array, and in that we are going to talk about syntax, memory layout, how to declare, how to define, and how to access a two-dimensional array. Let's start with a simple example. We had already studied one-dimensional array. For one particular student, if I want to store 5 marks for him, maybe physics, chemistry, mathematics, geography, history, something like that. So one dimensional array like this int a of 5 is sufficient. Now imagine if I want to store marks for one more student. So maybe I can grow it further. If we don't have the provision of a two-dimensional array, I can grow it further. So my array looks like this. Memory started from 200. This will be at 202. This will be at 204, 6, 8, and lastly 210. So my first five elements are sitting from 200 onwards up to 210 backwards. In this particular zone, these elements are seated. Now just with the single dimensional array also, I can logically remember that from 200 to 210 is student 1 marks like this. And that point onwards, I can have 5 more number of locations, and in that range, I can decide to store student 2 marks. So it will look like 210 to 212, 214, 6, 18 and 220. So first student marks are sitting between 200 to 210. Second students are seated between 210 to 220. In like that I can continue. And obviously this will be now something like size 10 array. It will be size 10 array. So just with the single concept of single dimensional array, I can grow infinitely like this. There will be no limit. Now, but the challenge will be, I should logically remember that up to first 5 is one compartment. Next is another compartment. Next is another compartment. So some marks from S2 should never get added into S1. Otherwise it will be a wrong total, something like that. So this kind of a storage, although is okay for storing the marks, is not logically good enough to represent the kind of logical compartment that we make in our head. So we need a facility that we want to visualize this as one linear growth, this as another linear growth. So our visualization requirements are that we don't want this to appear here. It's kind of, we don't want this to appear here. We want that stuff to kind of appear over here. So 210 onwards up to 220, just like that, we want to store the marks for second student. So in one dimension, when we grow linearly, it was another subject, another subject, another subject. And when we grow in this dimension, it is another student, another student. So it is like this. This dimension of growth is about marks. It's like on this axis we plot marks. And on this dimension we grow with student. Meaning the moment I start referring to another such a section, it is another student. And the moment I start referring to another such a section, it is another subject. That is why we call it as a two-dimensional array kind of a thing. Now we wanted this visualization, which means it will not be a size of 10, but it will be size of 5 and again maybe 5. Like this, we wanted the provision of double sizes. Like how many subjects you want to refer? How many subjects do you want to refer for one student? That will be meaning columns. And how many students do you want to talk about? That will represent the number of rows. So this is one entire row which has many column values. This is another row which has many column values. And we can have one more row which again will have many column values. In this particular example, since there are 5 number of subjects, I will keep the column value as 5, and let us, for the sake of understanding, make it 3. The first number here represents the number of rows that you want in the array, and this number here represents the number of columns that you want in the array. How many columns for each row? 5 columns for the first row, then again 5 columns for the second row, again 5 columns for the third row, and stop it because we just have only 3 number of rows. So this represents my row size and this represents my column size when I declare it. By the way, even if I had drawn these rows one below the other for our logical convenience, for our better visualization, better understanding, the memory provision remains the same. The place where the first row finishes 210, second row starts. The address where 220, the second row finishes, the third row will actually start. So this will go from 220 to 230, like that, 222 and onwards. Now, because it was an integer array, every element in the array will be integer. This is the significance of saying int over here. Saying A here means all this block together is referred by the name A. How many rows? 3. How many columns in each row? Is 5. Since we represent or write down the row size first, it is also called as row major form of giving the memory. So in short, for this what we have discussed is the memory layout. This is what we mean by the memory layout for the two-dimensional array. The memory is first given for the first row, then only memory is given for the second row, and then only we go on giving the memory for the third row. In other words, to give the memory for a given row, please give memory for all the columns in that row. I repeat, to give the memory for one entire row, we need to give memory for all column elements for that particular row. So this is row 0, column 1, column 2, column 3, column 4. So row index here is 0, row index here is 1, row index here is 2. For this row, column goes on varying from 0, 1, 2, 3, 4. For the row 1, columns again go varying from 0, 1, 2, 3, 4. For this particular row, again the columns vary from 0, 1, 2, 3 and 4. Thus we also see that if my row size is 3, the row index will never be 3, it will be maximum 3 minus 1, that is 2. If my column size is 5, then the column index will never be 5, it will be 1 less, that is 4 maximum. This is because in two-dimensional array also, we do 0 indexing. That is the first element in the 2D array is row 0, column 0, and then we grow. This was thus the memory layout. Now for example, if I am storing here 7, as you see in the diagram, I want to store a number 7 here in the second row and fourth column. I repeat, second row and fourth column. Second row meaning row index is 1, and fourth column meaning column index is 3. So I need to talk about something like 1 and 3 like this. So I can say A of 1, 3 is the method to refer to him. A of 1, 3 is the method to refer to him in this particular case. A of 1, 3 is the way to refer to this particular fellow. A of 1, 3 is the way to refer to this particular fellow. This is what is called as access. This is what is called as access of the array. So what we saw is how do you declare an array? Int A 3, 5, here is row size, here is column size. That is the syntax. This particular stuff is the memory layout. Declaration we had already seen how to declare that particular array. And how do you access one element? By saying the name of the array, rectangular parenthesis, row index, again another rectangular parenthesis and column index. First we mention is the row index, next parenthesis we mention is the column index. Now, just like one-dimensional array, this A13 we can use either for the sake of reading or we can use it for the sake of writing. So if I say A of 1, 3 equal to 13, this A13 appears on the left side of equal to. Because it is appearing on the left side of equal to, what happens is the right access. This means right access takes place. right access is taking place. Meaning, whatever is there already in A13 will be overwritten with the value 13. So what will come over here is 13. Another way, if I say k equal to A13, if I say k equal to 1 A13, meaning this particular A13 is now appearing on the right side of equal to. In this case, read access takes place. In this case, read access takes place. Meaning whatever is there in A of 1, 3, which is now 13, is just now modified, will be taken up and will be stored into a variable k. So k variable will now contain the value 13. So it is coming out from there. So either for reading purpose or writing purpose, we can use this particular syntax. Indexes are row index followed by column index. That's the way to access it out. Now, if I already declared int A35 and went on writing down values into that one by one, when I completely write all those values over here in this particular manner, like A13 equal to 13, A00 equal to 5, let us say A00 equal to 5, then 5 will come over here. Like that, I went on filling all the values by such sentences, statements. Then we can say array is defined or fully defined. Because every element in the array is defined, the entire array is also said to be fully defined. That will be called as the definition of the array. And this would be the syntax of that particular array. So in general, let me just summarize just to summarize whatever we said so far. Two-dimensional array memory layout is no longer different than one-dimensional array. It can be a single strip of memory given like this, but you are given the freedom to visualize two dimensions, two directions in which it grows. One direction grows the columns, the other direction grows the rows. One row is given the memory fully, then only the other row is given the memory. How to declare? This is the method to declare. And the first number is the row size, second number is the column size. Maximum number of rows that you want, maximum number of columns you want. Obviously, 3 multiplied by 5, 15 number of memory locations will be given. Since it was an integer, each element will require 2 bytes. If it was character, each element will require 1 byte. If it was float, each element will require 4 bytes. That way the growth will happen. Now how to access it? You just say A followed by row index and column index. In general, you will say A of ij. You can read it like A of ij. First rectangular parenthesis I represents row index. Second rectangular parenthesis j represents the column index. So this is an element in the ith row jth column. Of course, row counting started from 0. Column counting also started from 0. Now this particular syntax you can use on the left side, it will do write operation. You mention this on the right side, it will do the read operation. This is what we have seen so far about the arrays, two-dimensional array in such a particular situation. Now, if you know already how to reach out to one element, Aij, either for reading purpose or for writing purpose. Let's go one step beyond. Can I use this Aij in printf or in scanf? So I will write a small statement for you in that aspect. Say normally printf %d, and if I say over here k is some integer number, that k will be printed. K is just one integer. But if I now say Aij, no problem. A array, start from here. Ith row, I index is the row index, go there. J column index, reach out over there. For example, I can be suppose 2 and 3. If I is 2, I am in this row. J is 3, then I am here. This particular element suppose is 19. This value is suppose 19. Then printf %d Aij will print the number 19. Output of this will be number 19. Only thing to understand is how to reach out to every element of the array. Whether you use it for read operation or write operation or in printf or in scanf, rules for integer remain the same. Okay. So I told you how you can print all the elements of the array using printf. Now suppose these element values are not already given, you want to take it from keyboard. Of course you will use scanf. In case of scanf, we say scanf %d and some number %z. I want to take some value, or %z, %n. Instead of saying any single integer variable name over there, I can also say aij and I can say ampersand, because for scanf ampersand will be required because its L value needs to be generated, pointer needs to be generated. So using scanf %d ampersand a of j, you can take value in this. Suppose this is what you executed, scanf, and user type 21, then this old value will be lost, 21 will come at that particular place. That is the meaning of doing scanf on the two-dimensional array. So in this particular manner, I also told you how do you take input in a two-dimensional array, in one single element of the two-dimensional array, and how do you give output on the two-dimensional array. One method was taking input and the other was giving the output. Having said so much, let me tell you something more in addition to this. Why is it called a row major? You keep one row index same and go on changing the column index. So if you change the column index, the jump from the beginning address is a very short jump. Suppose my column index is 3. If my column index is 3, that indicates I skip 3 elements. But if my row index is 2, if my row index is not even 2, suppose my row index is 1, then row index 1 will indicate skipping one row or one row number of elements. But one row here contains 5 elements. So for the sake of skipping one row, I need to skip 5 number of memory locations. 5 number of elements I need to skip. That is why it is called as row major. Meaning row jump is a bigger jump, column jump is a shorter jump. Column index getting incremented will be a short jump. But row index getting incremented will be a big jump. Will be a big jump. I will give an analogy for this. If you jump the column index, it is like you are stepping up in the staircase. Jumping up the column index is similar to stepping up on the staircase. But jumping the row index is like you are directly jumping from one floor to the other one. Because one floor will have so many steps on that. That can be one analogical thing to visualize the difference between the column index jumping and the row index jump. Another example, suppose you go to a petrol bunk for filling petrol and you see on the meter 350. On the meter you are reading 350. The moment that meter is saying 350, you are not bothered about 5 much. You are not bothered about 0 much, because that is a less pain to your pocket. But the moment that 3 jumping to 9, that's a big jump. Because the significance of, that's what we call most significant bits and least significant bits. In the same way, we can say column index is least significant. It will require lesser or shorter jump. And row index is going to be more significant. That will require bigger jump from the beginning address. By the way, the beginning address 200 here is the same as A. Whenever we say A, it is treated as the beginning address 200, or it is called as the base address. Address calculation always takes place from the beginning of the array. Address calculation always takes place from the beginning of the array.